Hey guys, and welcome back to another GCSE science video. This time we're going to be doing a physics paper 2 because physics paper 2 kind of sucks, it's kind of tricky. But before we get started, most people that watch these videos aren't subscribed, so if you've ever found any of these useful at all, please consider subscribing as it really does help me out. Also, if you want, I have loads of spaces in my GCSE science and GCSE maths classes. If you're interested in joining those tuition classes, please check the link in the description. And lastly, my email address is in the description in case you have any questions about GCSEs or whatever at all. But without further ado, let's jump straight into this paper and try and walk through it as best we can. So the first question, we have a stretched spring which is elastically deformed, and it says what is meant by elastically deformed. Now there's two types of deformation that you need to know about in GCSE. One is plastically deformed and the other is elastically deformed. And what's the difference? Well, I like to stick with elastic because I think that elastic is something that's it's a word that's used a lot in day-to-day conversation. What does elastic mean? Well, if you have an elastic band, so a rubber band, or you have like trousers that have an elastic band in them, what does it mean? It means when you stretch them and you let go, it goes back to its normal size, right? So if you get a rubber band, you stretch it, you let go, it pings back together, right? That means that is what the definition of elastically deformed is. It will return back to its original shape when the force is removed. So it's the last one. So what's plastic deformation or plastically deformed? That is when you're using something like Play-Doh, for example. It's when if you squish it or you compress it, it does not return back to its original shape. So if I take something like a plastic bag, or I take Play-Doh or something like that, and I squish it up and I let go, it doesn't revert back to its original shape. It stays deformed. That's when it's been plastically deformed. Now, all objects will have a little bit of elastic deformation before it becomes plastically deformed. So with a spring, if you ever had a slinky, you may have seen this, but if you have a spring in your pen, for example, if you stretch it really, really far, eventually it will not return back to its original length. You have then plastically deformed it. So hopefully that makes a bit more sense. Describe a method to determine the extension of the spring. So here we have our system. This is a very common practical, which I'm hoping that you've all done, but it asks us to work out or state a way of measuring the extension. Now, how do you measure the extension? Well, hopefully you've done this before, but the idea is you first measure the original length, measure original length, and then measure the extended length. So what do I mean by that? Well, let me go back to the top and show you what I mean. You would take the mass off and you would just have a spring that's dangling. You'd measure its length, let's say it's 50 centimeters for argument's sake. Then you hang your mass on and you measure the new length, let's say it's 60 centimeters. Your extension is the difference between those lengths because it's gone from 50 to 60 centimeters. And then all you do is you do extended, take away original. And that is how you work out the extension of any object. And here we come on to the first calculation. The extension of the spring is 80 millimeters. The spring constant, essentially telling you how stiff the spring is 40 newtons per meter. So it takes 40 newtons of force to stretch the spring by a meter. Calculate the elastic potential energy of the spring, use the physics equation sheet. The equation that you'll be looking for is the energy is equal to a half kx squared, where x is the extension. Now you need to be careful with the units here. K is in newtons per meter, so we'll leave that as 40. But the extension is in millimeters, so I need to change that into meters. Now how do you go from millimeters to meters? Well, what I would do is I would go into centimeters, so you divide it by 10, so 8 centimeters. Then divide it by 100 to get to meters. But that is what you'd be doing for that. And again, you should get quite a small number, so let me just open up my calculator. So 0.5 or a half, depending on what you want to do, and then 0.08 squared, which is 0.128 joules of energy, which isn't a lot, but it's not really meant to be a lot because it's just a spring after all. For 3 marks, I think that's a pretty reasonable thing, especially because the equation is on your equation sheet. You just need to be able to find which one it is. This is a really common question in GCSE science exams where they ask you to get an equation which links 3 or however many variables, and then in the next part they ask you to use that same equation. So here, the equation, the way I call it is F equals kx, where x is the extension, but they've said here they want to use the letter E for extension. So the actual answer will just be KE. So on your formula sheet, it may give you KX instead, and you just need to change that to KE. Now it says a force of 300 newtons acts on a different spring. The extension is 0.4 meters. Find the spring constant. Well, if F equals KE, then if I divide both sides by E, that means F over E equals K. So that means K is equal to the force, 300, over 0.4. So that's over 2/5, which should be 750. Let's have a look. 300 over 0.4, 750. And then what are the units? Actually, we don't need to know because the question gives it to us force, but it is good practice to kind of get used to thinking about what units are in the odd case that they do not give them to you. Professional rugby players wear a tracking device that measures their velocity and their acceleration. Figure 2 shows a player with a tracking device, so apparently it's just on their back, on their shirt probably. The player is tackling another player who's running with the ball. Velocity and acceleration are both vector quantities. What is a vector quantity? Honestly, this is just a definition. It is a quantity that has magnitude and direction. So we're not just talking about the size of it. So for example, 10 joules of energy. We're also talking about which direction they're moving in. So for example, these players may have the same speed, but their velocity is in opposite directions because they're moving in opposite directions. This, if any of you want to do engineering or anything like that in the future, or maths or physics, vectors are going to be your bread and butter. They are very, very, very useful in real life. Then it says, which of the following is a vector quantity? Tick one box, which is quite nice because sometimes they just say tick all that apply. Distance is just a length, so it's not that one. Time only doesn't have any direction. Work done is energy, and energy is not a vector because you just say 10 joules, 100 joules. You don't kind of imply a direction. You also can't have negative. So that's something else about scalar quantities, is they aren't negative. We don't have negative time, right? We don't say that took you negative 10 seconds to do. With work done or energy, we don't say that's negative 50 joules. With distance, we don't say, oh, on a ruler, you don't measure negative 5 centimeters. But displacement absolutely can be negative because it's distance from a point. So you can have positive and negative displacement. That's just another way to think of it. Here we have a velocity time graph for the player running with the ball. Determine the acceleration of the player between 0 and 1.6 seconds. So when you have velocity time graphs or even speed time graphs or even displacement time graphs, you do need to work out a few different quantities from it. The way I do it is when I work out gradient here, I'm doing velocity over time. If you notice, acceleration is just velocity over time. So the gradient of that line is going to give me the acceleration. If I times the two quantities, so I found the area underneath the graph, that's velocity times time, which is distance. Or in this case, displacement technically, but whatever. So that's the way I kind of think about it. I think if I times the two quantities, what do I get? If I divide them, what do I get? Dividing is gradient, timesing is the area underneath. So determining the acceleration between 0 and 1.6, well, the velocity starts off at 0, so I want to put 0 there, and it ends at 4. So we have 4 take away 0 over 1.6 take away 0. I should be able to do this in my head, but I'm not going to. 5 over 2, so 2.5 meters per second squared. For 2 marks, I think that's pretty reasonable, but again, you need to use those tricks, finding the gradient, finding the area, which one makes the most sense for what you need to do. With something like this, it's always going to be either the area or the gradient. If it's acceleration, it's always the gradient of the velocity time graph. For 2.4, describe the motion of the player between 3.4 and 3.6. So 3.4 is this point here, and 3.6 is this point here. So as you can see, they are decelerating. And because it's a straight line, that means the gradient is constant, which means the acceleration is constant, which means this is constant deceleration. You can say constant negative acceleration, that is totally fine, because technically we don't have deceleration, technically, or large deceleration or something along those lines would work. For the next 3 parts, we have, again, a very stereotypical calculation question where they first say, hey, what's the equation? Then you're going to use the same equation. This is very, very common pattern. So the equation that links acceleration, mass, and resultant force, That is Newton's second law, absolute classic, absolute banger of an equation, F equals ma. And then it says the player accelerates at 25 meters per second squared, which is ridiculously fast. When a resultant force of 1800 newtons acts on her, calculate the mass of the player. Well, if we have F equals ma, and we have F equals 1800, mass we don't know, but we know A is 25. 25A. Then that means that A is just equal to 1800 divided by 25. Again, I should be able to work this out, but let's just leave it as is, shall we? 72 kilograms. And lastly, but certainly not least, we have the tracking device sends data to a computer during the game. So just one advantage of the data being sent during the game. Well, these types of questions are very hard for students to answer, and they're very hard for teachers to answer as well, because they require using, a lot of empathy, which sounds a bit weird, but you have to put yourself into the shoes of the people doing this. So why do they want the data in the first place? Well, to be honest, I don't know much about sports, but I guess the only reason why you'd want the data is because you want to monitor the players, right? You want to see how well the players are performing during a match. Okay, so why is it good, or why is it an advantage to send the data during the game as opposed to, well, what's the only other option? It's after the game, right? Well, if it's during the game, then that means you can monitor the performance during the game. Monitor the performance live. As opposed to having to wait until afterwards. So you can imagine that the coach maybe is looking at this data in real time, or whoever looks at the data, I actually don't know, to be honest. I guess like a physiotherapist or something will be looking at this data whilst the game is going on, which means they can give immediate feedback after the match. That would be my guess, but this is kind of the idea. So you need to kind of break it down. So first of all, why do they need the data? Well, they're obviously monitoring the players for some reason. I don't know the reason. I'm going to be honest with you. Maybe it's for injuries, maybe it's for how they can be more efficient, whatever, right? Then it says an advantage of it being sent during the game. Well, what's the opposite? What's the only other option? Well, sent after the game, right? It can't be sent before the game because the game hasn't happened yet. So why is that an advantage? Well, the only difference between sending it after the game and during the game is one is live and one is not live. So that's why I've written the answer monitor performance live. And in the mark scheme, it does say performance can be monitored during the game. So potato, same thing. Okay, so for question 3, we have waves, which again is a pain in the butt topic for a lot of students. So a student made water waves in a ripple tank, and as you can see, I've drawn an excellent one-to-one recreation of this. So we have the water tank and we have these waves. They will appear as dark patches, especially if you put a light underneath it, which is what a lot of people do to make a shadow, but whatever. Describe how the frequency and wavelength of the water waves can be measured accurately. So, first things first, if you want to measure wavelength, I like to think of the units. So frequency is measured in per second, or hertz, and wavelength is measured in meters. So what we're going to do is we're going to start with the wavelength, because I think that that's a nice place to start. We're going to place a meter ruler along the side of the tank, like this, and we're going to measure the full length of the tank. So place meter ruler. It's probably best to say like along the wavefronts or perpendicular to the wavefronts. Perpendicular to wavefronts. Those black lines are wavefronts, by the way. And we're going to measure the length of the screen. Measure length of screen. Measure length of screen. All we're going to do is that the wavelength is equal to the length of the screen divided by the number of complete waves. Now I'm going to explain this to you complete waves. What we have here, the black lines are the peaks, and the reason for this is if I show you what this looks like from the side, it'd be something like this. So I'm going to try and match it up as best I can. Right. These peaks here are the black lines. which means between them is you have the troughs, right? The parts of lower displacement. Hopefully that makes sense so far. Now, if you remember what wavelength is the distance between adjacent peaks or adjacent troughs. So all you need to do to work out the number of complete waves is you go 1, 2, 3, 4, 5, 6. You basically just count the number of pairs of black lines. That's it. And then when you're dividing it, that just gives you the length of one of them, which is the wavelength. The frequency is a bit more interesting. Don't forget, as you're doing this, these waves are constantly moving. So to do this first part, you'd most likely either need to take a photo, or I guess you could do it normally if you managed to create standing waves, but yeah, let's leave it as that. For the frequency, here's what you need to do. The first thing is, it's in per second. What do you know of that counts seconds? Well, we're going to use a stopwatch. Right, because that counts seconds. That gets you one of the marks. Now, how are you going to do this? What you're going to do is you're going to record and count, using the recording, waves passing a point each second. So if it's 5 waves per second, then your frequency is going to be 5 hertz. And that's literally it. Yeah, that's basically it. So I hope that makes a bit more sense now. The student recorded values for the frequency and the wavelength of waves in the ripple tank. Table 1 and 2 show their results. We've got the frequency in hertz, 9.8, 9.4, 9.3. Then wavelength in centimeters, 1.7, 2.2, and 2.1. And it says determine the mean wave speed. Now, in order to do this, all you really need to do is, first of all, we need to write the equation, which is v is equal to f lambda. We are going to have to convert this lambda into meters, because don't forget we want the answer in meters per second. And now when it says the mean wave speed, that's because they have 3 values. Now, I'm assuming that your science teachers have been very good, which it's a bold statement, I know. But we need to calculate the average of these. So the whole point of taking 3 readings is that you can average them afterwards. Now, I will say this looks a bit anomalous, but it hasn't said that there's any anomalies, so I'm going to just say, I'm just going to work out the average for each of these. For this one, it should just be 9.5, right? But let's say you didn't know that. The mean is you just add up the values, so 9.8 plus 9.4 plus 9.3, and you divide it by the number of values, in this case 3. Let's see if I was right, 9.5. So the average there is 9.5 hertz. Let's do the same for the centimeters. So we have 1.7 plus 2.2 plus 2.1 divided by 3. We get 2, so 2 centimeters for the wavelength, which again we need to convert into meters by dividing by 100. And then all we're doing is doing 9.5 times 0.02, which is something. And we get 0.19 meters per second. Which again, bear in mind that this is a water wave, right? So it's not exactly going to move super fast or anything. It's water. But yeah, that's it for 4 marks, which I think is fairly reasonable. I think this is one of the harder calculations because you have to do the mean first. But remember, if it says mean, and if they've given you 3 different readings, you need to work out the average, because that's the whole point of getting 3 readings, right? Hopefully your teachers have shown you that in every experiment that you've done. So, this is a really good question, kind of at the heart of a lot of science. What is the advantage of taking repeat readings and then calculating a mean? The idea is to reduce the effect, and it is important that we say the effect, of random errors. The reason why I say reduce the effect is because random errors are random, we can't actually predict them, right? Because they're random, that's the whole point. And so we can't guarantee that taking a mean of 3 values gets rid of the random errors at all, but it will reduce their effects because since they're random, let's say, for example, in these values here, this is 0.1 bigger because of a random error, this is 0.1 smaller, and that's 0.05 bigger. Because they're in different directions, some of them make the numbers bigger, some of them make them smaller, they cancel each other out a little bit. Not entirely, or at least we can't guarantee it will be entirely, but they will at least a bit. The speed of the wave is affected by the depth of the water in the ripple tank. This is not something you're expected to know. The deeper the wave, the deeper the water, the faster the wave. Explain how the depth of the water affects the wavelength if the frequency is constant. So again, this isn't necessarily something you would know, but they're relying on you being able to use science, use the equations we've got to make predictions. So they're talking about the deeper the water, the faster the wave. So in other words, velocity is increasing. But it says that the frequency does not change. So how does it affect the wavelength? Well, if v increases, but f stays the same, lambda also has to increase. The wavelength also has to increase. I mean, let's think about it, right? If v goes from 2 to 3, but f stays the same, lambda has to increase, right? There's no other way. So in other words, wavelength must increase. Because of this. Because of that formula there. That's all you need. Oh boy. Probably the least fun part of physics. I'm just going to point something out, by the way. GCSE, everyone hates magnets. A-levels, everyone hates magnets. When I was at university doing my degree, everyone hates magnets. Magnets suck, and they are... Honestly, they're not that well understood, really. There's a lot of kind of missing information about them. So if you are interested in doing like physics and things like that, magnets are very odd, and so they might provide some kind of interest to you. But yeah, everyone hates electromagnetism. It's a universal thing. Even at university, even the grumpy old professors, magnets suck. But we have a magnetic field pattern, and it says, where is the magnetic field of the magnet the strongest? Now, if you've ever used a magnet, like played around with it, you might know this just from experiencing it, right? Just messing around with it yourself. But here's how you can tell. The closer together these magnetic field lines are, the stronger the magnetic field. So if I look over here, I have 5 lines packed together, but over here I have 3 lines that are quite spread out. And over here, again, it's like 2 lines that are quite spread out. So in other words, where are the lines the closest together? They're the closest together at the poles. Now, the reason why I won't just say the North Pole or the South Pole is because at both poles, they have kind of an equal field strength. So all you have to do is write at the poles. And again, that is entirely dependent on how close together the field lines are. Then says, how does figure 4 show that the strength of the magnetic field is not the same at all places? Well, it's just what I just said. The strength of the field is how close together the field lines are. So why is it not the same everywhere? Well, if you notice, look at the distance between the field lines. It changes everywhere. So it gets further apart in different places. So all we have to do is say, because the distance between field lines varies. Between field lines varies. That's why the magnetic field strength is not the same everywhere. And the strength of the magnetic field is not the same everywhere, because the distance between the lines changes. Figure 5 shows an electromagnet being used to separate iron and steel from non-magnetic metals. Explain one reason why an electromagnet is used instead of a permanent magnet. So it says explain one reason. So what that means is you're only saying one positive, but then you're saying why it's a positive. Okay? So some people try and give 2 different reasons and they think it'll give them 2 marks. It won't. It will give you 1 mark because they're asking for one reason and an explanation. So what I like to do is I like to have a bullet point. What's the reason? Well, what's the difference between an electromagnet and a permanent magnet? The only difference, really, is that you can turn off an electromagnet. That's it. Turn off an electromagnet. Right? That's kind of the key point. Now, why is that useful? Well, what are we trying to do with this? So we put this electromagnet over a conveyor belt, and all of the magnetic metals, so in this case they're just talking about iron and steel, will get stuck to the electromagnet, whereas the rest of the metals just go off to wherever they're going next. So Of course, the problem is eventually it's going to get full. Right? There'll be too much metal on the electromagnet. So we need a way of removing the metal from the electromagnet, right? Logically. Well, the easiest way is to turn it off. Because when you turn it off, it'll just drop. That's it. I like to think of it almost like you have a claw to grab something, right? So you have this hand, and it grabs stuff from the conveyor belt. But if it can't open again, it's kind of pointless, because then you have to break it to kind of let go of the thing. You have to use a lot of force to open up the hand again, so to speak, or the claw. So the purpose of this is to easily remove the iron and steel afterwards. That's the point. Hopefully that makes a bit of sense. It then says pieces of iron and steel are attracted to the electromagnet. Name 2 other metals that would be attracted. There's a few, but probably the most common ones are cobalt and nickel. So given that the design of the electromagnet, so the actual shape of it cannot be changed, give 2 ways in which the force exerted by the electromagnet could be increased. So if you remember, you have a few equations, like you have, for example, BIL as an example. Now, since they're saying that the actual design cannot be changed, that means B can't really be changed either, nor can the length, so we could increase the current. In the electromagnet. The next one's a bit trickier, because as we've established, we can't change the field strength, we can't change the length, we have to change the current, but what else could we change? Well, simply put, we could bring the electromagnet closer. Closer to the conveyor belt. Because then the iron and steel are closer, which means the force is stronger. Because as we know, as you get further away from a source of a force, it gets weaker. Things like electrostatic and gravity and things like that. Here we are, the motor effect, or the generator effect, depending on how you want to look at it. People hate this. People really, really hate this. But the conveyor belt that moves the pieces of metal is driven by an electric motor, which is, it looks exactly like this, where you have an alternating current going through this, which spins the wire, because it's in a magnetic field. The length of the wire AB is 120 millimeters, so I like to label that L. Don't forget we want to change that to meters, so that would be 12 centimeters or 0.12 meters. God. The current is 4, and the force is 0.36. Calculate the magnetic flux density, which is B. So we're looking for an equation that links F, B, I, and L. That is, force is equal to Bill, which means the magnetic flux density is force over IL. And we just sub in the values for 5 marks. 5 marks. Crazy. Absolute insanity. IL, so let's do 4 times 0.12. So that'd be 0.36 over 0.48. That would just be 3/4. 0.75? I'm pretty sure it's 0.75. But let's not be arrogant. We have a calculator, so let's use it. Oh. Too easy. Now, that actually gives us 4 marks because we have to give the unit. So as I said earlier, they do not always give you the unit. So what is the unit in this equation? It is the Tesla. So capital T, Tesla. And for the last bit, we have an absolute classic. The thing, we're throwing up gang signs in the exam with the different forces and stuff. We have Fleming's left-hand rule, which can be used to determine the direction of the force on the wire AB. Complete the labels. So how do I do it? Well, there's a few different ways. This is the second finger, right? And if you notice, it has a C in it. So second is the current finger. The first finger, it starts with an F, and so that is the field lines, or the field. The magnetic field is what I'm trying to say here. For the thumb, I don't really have a really good one, but it's like it's a force. I have heard it said as like the thumb, since it begins with TH, it's called the thrust. But I don't know about that. That's a bit weird. Doesn't really make sense to me. But yeah, first finger is the field. Second finger is the current. Thumb is the force. Yeah, that's just how I do it. To be fair, if you have the two others, then you just know the last one is the force. That's just the way it is. I like the second finger being the current, the first finger being the field, and then it's just the other one is the force. In the future, if you guys do A-level physics or even university level physics, you have a right-hand rule as well. But you can actually use this for any sets of related vectors, which I think is pretty cool. So now we're going back to the electromagnetic spectrum, and we have different parts used in medical imaging, cool. And we have this infrared camera, which basically detects temperature change, as you can see here. So the dark bits are like 23 degrees, which is, let's just say room temperature. And then it goes all the way up to 34 degrees, which is apparently the temperature of this dude's hand, at least 3 of the thick fingers. The other 2 are a lot colder, which is interesting. Probably due to blood flow, I'd say. Explain why the infrared camera is able to show that parts of the hand are at different temperatures. So this comes to what is infrared radiation. Infrared radiation is released from hot objects. So infrared radiation, or different temperatures release different amounts or intensities. Whoops, I forgot to write different. Different amounts or intensities we should really use the word intensities because we're being very scientific, of infrared radiation. So essentially hot objects release a lot of it, and cooler objects do not release as much of it. So, you know, when you're very hot, so maybe after you've just done a lot of running or something like that, you've been out in the sun for a while, you can sometimes like feel the heat coming off your skin. That's infrared radiation. Whereas in like the winter, for example, you're very, very cold. Now, this difference is picked up or represented on the camera. Differences are represented as different colours or shades. As different, should we say shades or colours? I want to say colours because it goes from black to white, unless you consider black and white shades, which maybe it's a colour gradient, right? Yeah, that's essentially how it works. It's very useful in different conditions. So some people use it for like picking up the presence of human beings in buildings. If there's like a building collapse or something like that, they sometimes use infrared cameras to try and pick that up, and various other things. This is the bit that a lot of students have trouble with. Infrared has wavelengths from 700 nanometers to 1 millimeter, so 1,000 nanometers basically. Which parts of the electromagnetic spectrum would have waves with a wavelength of 6.5 times 10 to the minus 7? Pretty much anything with times 10 to the minus 7 is visible light. It's tricky. It's very tricky to know all of these. I don't really think people should have to learn all of these because it's a bit arbitrary, but it's part of the spec. It's something you have to do, but the good news is there's normally only 1 mark to do with it in each paper. And here's a big one. In hospitals, we tend to use X-rays, which I'm sure most of you will either have very soon or have had in the past. The reason why I say we'll have very soon is when you hit 18, when you have your last dentist appointment for free on the NHS, they take a X-ray of your mouth to kind of have a track of your position of your teeth and things like that. But they also use gamma rays, which I doubt most of you will have had before, which is handy. So for X-rays, a machine produces a brief burst of X-rays and that's it. It produces a picture, which is basically the same way as how a camera works, where it has a flash of light and it produces a picture. We have a flash of X-rays, which produces a picture for an X-ray. To use gamma rays, however, you need to inject a radioactive isotope into the blood, and the gamma rays will come out of that radioactive isotope as it passes around your body. So the idea is you can then see the exact blood vessels going through a person, whether it's, in this case, it looks like it's in someone's leg. They do this a lot for imaging the brain and the heart as well, because those tissues do not show up very clearly on X-rays, so instead we need to use something else. This is really, really useful because it shows you, it traces blood vessels. So you can see if there's any internal bleeding or if there's any kind of aneurysms or something like that. Super, super, super useful. But compare the potential risks. Obviously so I'm actually going to type this just to make it a bit easier. In terms of comparing the risks, both have a risk of ionizing radiation. Right? They both have a risk of cancer due to ionizing radiation. So X-rays ionize your DNA, as do gamma rays, and so they both can cause cancer. That's just a sad fact of life. What else? Well, when you think of the X-rays or with gamma rays, essentially with gamma radiation, the whole body is irradiated, whereas X-rays only affect kind of the exposed part. So what I mean by that is, even though this gamma imaging technique here is only for this person's leg, it looks like the knee, because you're injecting it into the blood, the gamma radiation is all over your body. Because when you inject something into your blood, it only takes a few seconds for that to pass completely around your body, continuously releasing gamma rays. With an X-ray, they normally only need an X-ray of a very specific part. So here it looks like this woman's abdomen, so maybe her spine or something like that, or her rib cage. So you can basically keep the rest of the area covered, right? Her head is not going to get any X-rays. Her legs aren't going to get any X-rays. Same with when you get that dental scan when you're 18. It's only going to affect your head, right? Or your teeth. It's not going to affect your chest, your legs, anywhere else. So in that case, there is less exposure in X-rays than there is in gamma rays, because the gamma radiation has to pass around your entire body. So the radioactive isotope has to pass around the entire body. Yeah, so that's kind of a big thing. And the last thing that you really need to say is that the exposure time for gamma rays is longer. Sorry for the double E's, by the way. I think my keyboard's breaking and it's starting to type random amounts of E's. The reason why I say the exposure time for gamma rays is longer is this procedure here takes a hell of a lot longer. Again, when you do that dental scan, if you've ever had an X-ray before, it is extremely quick. We're talking about seconds. Like the dentist or the doctor will leave the room, flash, done, that's it. Whereas with this machine here, it takes an image over a much longer time scale. And of course, even if this imaging didn't take that long, you've still injected a radioactive isotope into your blood. So even after you've left the imaging machine or whatever, or even the hospital, you still have some of that radioactive isotope in you. The reason why I've only put 3 bullet points, even though we had 4, is technically this is a second point. X-rays only affect part of the body. So we've kind of done, in 3 bullet points, 4 marks worth of answers. For this question here, we have X-rays are produced by colliding high-energy electrons into a metal target, which is very cool. Electrons have high energy because they're accelerated to very high speeds. But only a small portion of the kinetic energy is converted into an X-ray, because the rest is scattered off or released as other types of energy. An electron is accelerated through a distance of 15 millimeters, so that's distance. The work done is 1.2 times 10 to the minus 13. Work out the force. So we have F, W, and D. That is, work done is equal to the force times distance. So it means force is equal to work done over distance, which is going to be a very, very small number. Over 15. Okay, we could write this as times 10 to the minus 3, or we can change this into centimeters and then change it into meters. So let's just do that, because I don't want to... Oh, there's another 0, Mitchell. Come on. There we are. Again, some of these equations you just have to kind of know, but I do think that the most effective way to learn the equations is obviously to have a formula sheet in front of you whenever you're doing questions, and label the variables they give you and the one that you want. And then all you're kind of doing is looking through the formula sheet for an equation that has the 3 or 4 or whatever letters that you have. So F, W, and D, if you look on the formula sheet, W equals FD. That's it. So it's kind of like a treasure hunt, I guess, kind of. They're 8 times 10 to the minus 12 newtons. Again, I love the calculations in GCSE science. Very nice. Assuming you know the equations, but hopefully now I've shown you a way on how you can find which equations you need to use. Now, the metal target is usually made from tungsten because it has the highest melting point of any metal. So why does this enable the X-ray machine to be more powerful? Well, again, look at what they've given you. They've told you it has the highest melting point. That must be relevant. So in this case, well, if you imagine you're hitting this metal over and over and over and over and over again, the metal is going to heat up. It also says it enables the X-ray machine to be more powerful. So that means the X-rays are stronger, which means the electrons are hitting it even harder, harder and harder and harder. Well, as you can imagine, some of the energy from the electrons is transferred to the metal, which means it heats up the metal. So, I mean, basically, I've just given you the 3-mark answer already. So, some energy from electrons. Oh God, come on. Heats. I'm pressing the E first, I promise you. Heats up the metal. So some of the energy from the electrons heats up the metal, which increases the temperature of the metal. So using a higher melting point metal enables more electrons to be collided per second than a different metal, which would melt. That's basically it. It's pretty cool. Pretty cool. So here is a very interesting question. This is the last question, but it's only 2 parts because each part is worth a lot of marks. So scientists are developing a hypersonic aeroplane that will travel much faster than normal aeroplanes. An aeroplane accelerates from a low speed to a high speed with the engines at maximum power, but the acceleration is not constant. Why? Well, the forward force of engines is constant. So you might think, well, hang on, that means the acceleration is constant. But think about what happens. Now, as you speed up, the overall force that we use in F equals ma is the resultant force. So we're going to have the driving force of the engine minus, well, what force is opposing aeroplanes when you're moving through the air? It's air resistance. So I know that this part is constant. The driving force is constant. But the air resistance will change. So as velocity increases, the air resistance also increases. This reduces the overall, resultant force on the plane, which decreases the acceleration of the plane. So, as this plane speeds up, the air resistance will increase. This means this number here, the driving force minus the air resistance, decreases, which means the acceleration decreases. I should probably add, because mass is constant, so the mass of the plane should also be constant. But yeah, that's the essential reason. So although the driving force is constant, the overall force acting on the plane is not constant. Because as it speeds up, the air resistance, the air is trying to stop it more and more and more. The air resistance increases, which means the acceleration will drop. They give us a lot of information here. The hypersonic aeroplane will have jet engines and a rocket engine. The speed is measured on a uniform scale called the Mach scale. Basically, Mach 1 is 330 meters per second. This is just the speed of sound. So Mach is how many times the speed of sound you're going. So this is 5.5 times the speed of sound. That's 25.5 times the speed of sound, which is crazy. And the resultant force, calculate the mass. So we're going to be using F equals ma. Whoops. But all they've given me is they've given me a change in velocity, a time, a force. So we don't have the acceleration, but remember, acceleration is just the change in velocity over time. So that has How would we write this? 25.5 minus 5.5. But then we're timesing it by 330, right? Because that's the actual speed that it's going at. So that's 20 times 330, which is 6,600 over 300 seconds. So that's the acceleration, right? So we have 25.5. Because again, that's the actual speed. The difference in the Machs times 330 over 300 gives me 22 meters per second squared, which is actually really, really quick. Then F equals ma, so that means m is equal to force over acceleration, which is 630,000 over 22. I don't know the answer to that, I'll be honest. 630.23 divided by 22. Okay, we're going to round this to two significant figures. So we look at the second non-zero number, which is 8. The number next to it is bigger than 5, so we're going to make that 29,000 kilograms, which is, yeah, that's pretty heavy. It's not that hard, right? It's not rocket science, get it? Rocket science? Rocket engines? Okay, so that brings us to the end of the paper. I think that paper is pretty good. Question 6 is definitely very hard. The calculation is a bit of a monster. But again, label what they've given you, label what you have, and label what you want. I didn't actually label what I wanted in that case. And then look at the equations you have to try and work things out. I think that is very difficult. But I hope that explains things a bit better for you. I hope that makes a bit more sense. I hope that gives you more confidence. If it has, again, please be sure to subscribe, because it does really help me, or like the video, share it, etc., all that fun stuff. But I will see you in the next one. Best of luck in your revision.